Hey you guys, so in this video we're going to just do an example problem. Using our calculator, we're going to plug in some data. This problem's on page 156 in your binder, so start by pausing the video, take out your binder, get to this page, take out your calculator, and the first thing you're going to do on your calculator is input this data into a list and spreadsheet page. So go ahead, pause the video while you do that. Alright, your screen should look like that with a bit more data at the bottom that you can't see. And then we are going to add the second page to make the scatter plot. So go ahead and make your scatter plot. Alright, your scatter plot should look something like that. I went ahead and I made the best fit line and the residual plot on there. So once we have that, we're going to make our own kind of sketch of the scatter plot. So when I do that, it's just going to be a pretty simple sketch, like that. And all I care about is the minimum and maximum values for each, the x and the y. So if you look at the scatter plot on your calculator, the x variable goes from 60 to 74. And the y goes from, 170, but that's a little bit up. So 170 to 230 towards the top. Okay. We do need to label these. So this is height. And this is weight. And when you title it, it's always y versus x. So weight versus height. And maybe if we want to get it to be more specific, we'll call it Lego weight versus height. And now we're just going to kind of sketch out as nicely as we can the points that are on there. There's about 7 points. And they're a pretty straight line. They seem to have a little bit of upward curve to them at the end. Kind of like that. And then I'll put in my best fit line, just like on the calculator. That comes basically from the corner and straight through like that. Okay? So that's all that I'm looking for in the sketch. All right. What is the equation for the LSRL? Well, it shows up right on your screen there, but we want to remember write it in context. So instead of y, I'm going to write predicted weight. So predicted weight with the little hat on top for predicted equals, and we can round it to 2 decimals, so 5.69 times height plus negative 188.89. Okay. All right, so from there we can already see what the slope and the y-intercept are. So when I state it, I just literally write m equals 5.69 over 1. It's going to help to write it over 1, and I also recommend putting units there. Okay, weight and height. Height was measured in inches per, and weight was measured in pounds. Okay, so inches per pound. So using the template that you got today in class, we say the model predicts. The model predicts for every, and now I need to say 1 and then the x unit. So 1 inch increase in height. For every 1 inch increase in height, the weight will increase, and we say increase because it's going up, by, and then we use that slope amount, and we say weight will increase by 5.69, and and then the y unit, which is pounds. Okay, so that's what the slope means. The model's predicting for every 1 inch increase in height, the weight is increasing by 5.69 pounds. So we can do the same kind of idea with the y-intercept. So the y-intercept appears to be, it's at negative 188.89 number. Okay, so the y-intercept I'll write as the 0, comma, negative 188.89. And we use kind of a similar format. The model predicts, but this time we say when x is 0. Okay, x is height. So when height is 0, the weight will be negative 188.89. The weight will be negative 188.89 pounds. Right? And immediately your brain should be going like, that's kind of weird. That doesn't make any sense. And it doesn't. And part P of this problem, question P there, says, does it make any sense? No, it doesn't. You can't have a Lego set that doesn't have any height, and you can't have anything that has negative weight, right? So no, this doesn't make sense. Then the next question talks about the correlation coefficient, right? For this, we're going to need a new page on our calculator. We're going to have to get to a calculator page. So Control Doc, get to a calculator page. And remember, you can go press the VAR button, and then you're looking for stat.results. And when you do the stat.results, you get this picture. Right, there it is. Let's make that much smaller. There we go. Okay, so we get that picture there. And it tells us the same slope and y-intercept we're using, but it also gives us the r value, which is 0.995, which we'll just call it r equals 0.99. So here we go, r equals 0.99, and we're also supposed to interpret the correlation coefficient. All right, this is where we say whether it's strong, weak, positive, negative. Okay, so we say there is an, or this one is strong. So we say there is a strong, positive correlation. There's a strong, positive correlation between height and weight of Legos. Okay. So next it asks us to create a residual plot. We already did that. Woohoo! Here it is. Okay. So pause the video, take a second, and sketch that out. Does not have to be very detailed, but should have that -4 and 4 on there, and your axes should be labeled. All right, there's what mine looks like. So yours should look similar. So the next part here says, based on the correlation coefficient and the residual plot, is this model appropriate? Well, this is where we decide, are we going to go 0 for 2, 1 for 2, 2 for 2? All right, so I look at two different things here. We've got the residual plot shows a curve. Okay, that's not great. We don't like that. Right, it's not randomly scattered. It's got kind of a U shape, so that's not so good. The R value, though, was very, very strong, 0.99. So it's kind of a 1 for 2 situation. It's okay, it's not great. So we'll write a little sentence here that says something like, this model is okay, but could be better. since the R value is strong, but the residual plot shows a curved shape. All right, just a few more questions. The next part says find the residual for a structure that is 66 inches tall and has a weight of 150 pounds. Okay, so the residual means I have to use that formula. Residual equals observed minus predicted. Okay, and the observed is what they give me in the problem, 150. So it's going to equal 150 minus, and now I need the predicted value for a height of 66 inches. And here's where we've got to jump onto our calculators again. And on your calculator, you're going to still use the calculator page and hit the var button again and look for stat.regression, regression equation. And when you type that in, we want to find out what is the line or equation going to predict for a structure that is 66 inches tall. So I got to plug in 66. So your screen should look like this. So it looks like this. You got your stat.regression plugged in 66, and it gives us an answer there, 186.35. So I'm going to move this over here. All right. So now my this model predicts that a structure that's 66 inches tall will have a weight of 186.36. So right here, I'll finish that off, 186.36 pounds, 186.36 pounds. And when I do that subtraction, that would equal negative 36.36. That's the residual. That means we had an over prediction. The line was predicted, or the line predicted 186 pounds. The actual weight was 150. All right, and then in our final two questions here, okay, we have a structure that is 63 inch has a residual of 23 pounds. Describe what this means in the context of the situation. So I want to look back up here at my formula. Observed minus predicted is saying, ends up with a positive number, 23. So if I'm going to do observed minus predicted and get 23 pounds, that means the observed value had to be bigger than the predicted. So that's what we write. The observed weight was bigger than predicted. And finally, we're going to use the model to predict the weight of a structure with a height of 71 inches and then a height of 95 inches. Okay, so do the same thing, stat.regression with 71, then with 95, and see what you get. So you should get 214.78 and 351.24. So let's move this off to the side here. And we'll copy those down so that I get 71. Oops, undo. 71 leads to a weight of 214.79. And 95 leads to a weight of 351.24. All right. Now, when it asks how much faith do you have in these predictions, some faith, because it was an okay model, but it wasn't a great model. But one of the things we got to watch out for is this 95. If you go back and you look at all the data we collected, the biggest height was 73. The biggest height here was 73. And 95 is way out of that range. 71 is within the range, but 95 is way out of that range. So we're not going to have a lot of faith in that 95-inch structure, head weighing 351 pounds, because that's called extrapolation. So we don't have much faith. Not much faith. It's too far out of our data range, so we don't know if the pattern continues or if maybe taller structures get a lot more heavy, which seems possible. All right, I know it was a long video. These problems do take a while, but I hope this was helpful. Thanks for watching.